This is the Calc 1 lecture for areas. It's the second of two parts of the area lecture. So please turn to page 7 in your notes. So we are going to work on one question where we again work with vertical representative rectangles. And then I'm going to explain to you when and how we would use a horizontal representative rectangle to find the area between two curves. So our question is asking us to find the area between the curves y is equal to 1. That's this horizontal line right here. Between y is equal to x. That's this blue curve right here. And y is equal to 1/4 x squared, which is actually a parabola that would look something like that. Now, I'm only supposed to do this for the region between 0 and 2. So do you see that the shaded region I am looking at would be in here? I'm often asked, why can't we do this region in here? It's not bounded by all three of those curves, so I am not using this region. So let's label my curves. I have y is equal to 1. I have y is equal to x. And I have y is equal to 1/4 x squared. Now let's draw in a representative rectangle that's vertical. Remember the steps: sketch curves, shade in the correct region, draw in a representative rectangle, and slide it. Slide from 0 to 2, back and forth. Focus on the top of the representative rectangle. As you slide, do you see that once you get to 1, the curve that's on top of your purple representative rectangle is now blue? It is no longer red. The bottom stays on the green curve the whole time as you slide from 0 to 2 back and forth. But the top of the purple representative rectangle changes from a blue curve on top to a red curve on top. So therefore, if I want to use a representative rectangle that's vertical, I need to separate this region into two pieces. And I need two integrals. I need one for the blue curve on top, and I need one for the red curve on top, and I am going to need to add those two integrals together. Please remember that when you have a vertical representative rectangle, that you slide right, left. You get your boundaries from the x-axis. Oh, good. Let's go ahead and do that now. My blue integral would go from 0 to 1. My red integral would go from 1 to 2. please remember that your equations need to be solved for y. Okay, they are. On the blue representative rectangle's top, I have an X. That's at the top. Remember, it's upper minus lower. Let's write that down too. Upper minus lower. So here's upper. The upper curve is y equals x. The lower curve is 1/4 x squared. Now let's go to the red curve. Here, lower. So for my red curve, my upper, y is equal to 1 minus, and my lower is 1/4 x squared. I am assuming that you could do this integration. I want to start focusing more and more and more on setup. Now, if you turn to page 8 in your notes, you may think there's a mistake because the problem is exactly the same. I am still looking for the region bounded by y equals 1, y equals x, and y equals 1/4 x squared. So here is my shaded region, because again, I asked to go from 0 to 2. But this time, I want to draw in a horizontal representative rectangle. I want you to focus on the right end of the horizontal representative rectangle and the left end of the horizontal representative rectangle. You don't have to write these down on your notes. They're at the very bottom of the page. I want you to slide this thing, this representative rectangle, up and down. That's how I want you to slide, up and down in your head. And I want you to focus again on the right and the left ends of this representative rectangle. Does the purple representative rectangle stay on the green curve as you slide from 0 to 1? Does the left end of the purple representative rectangle stay on the blue curve as you slide from 0 to 1, up and down? The answer to both of those questions is yes. This means that I now find my boundaries not by looking at the x-axis, but I find my boundaries from the y-axis. Because I do not have, well, okay, let's just leave it like that for a minute. Now, let's talk about my equations. My equations need to be solved for x, not y. In other words, this thing is not f of x. that green curve. It needs to be f of y. Same for all three, well, both curves, the green one and the blue one. So what I'm trying to tell you again is that you are not solving for y. Can't use y equals 1/4 x squared. You can't use y equals x. You need to solve those for x. So let's do this one first because that's really easy. Isn't that just x is equal to y? Yay, okay, done. Now, let's solve y equals 1/4 x squared for x. I would get 4y equals x squared. When I take the square root of 4y and the square root of x squared, I get x equals plus or minus 2 square roots of y. So this equation here, x equals. All right, guys, let's see if I can show you this. This part of the curve is x equals positive 2 square roots of y. This part of the curve over here is x equals negative 2 square roots of y. I'm not using this part of the curve over here. I'm not using this thing. I am using this. So when I set up my integral, I am going to do right hand side of my representative rectangle, so that's my green curve. So that is 2 square roots of y minus the left hand side of my curve, so that would be y. Now guys, don't stick a dx here. You're not integrating with respect to x when you have a horizontal representative rectangle. You are integrating with respect to y. Your boundaries come from the y-axis, so from 0 to 1. So what's the benefit of using a horizontal representative rectangle instead of a vertical one? Well, if you remember on the previous page, this required us to have two integrals when I did a vertical representative rectangles there. But my curves were already solved for y here, so that one was set up kind of to be able to be done pretty easily with vertical representative rectangles. You also might get something where you cannot integrate when you have your curves solved for y equals, and you can when they are solved for x equals. So we'll talk about that a little more, and you'll see more of that as you get into Calc 2. But let's look at first of all, let's look at this. Let's use a different color. Let's look at my transparency here. Let's put in a representative rectangle that's horizontal. Guys, this right here now is my change in y. This, which is my width. This is my length. It's my g of y right here. and my f of y over here. So my integral would be from C to D, right minus left dy, length times width, summing up an infinite number of them, those horizontal representative rectangles, as they are getting skinnier and skinnier and skinnier. Okay, here is your information that was at the bottom of page 8 for your horizontal representative rectangle. The other thing that you might want to add to this is that you will have dy here, just like on your vertical representative rectangle, you have dx. All right, now let's look at page 9 of your notes. Find the area of the shaded region. You have the equation y equals 2 here. You have this curve right here, which is y equals secant squared t. And you have this curve right here, which is y equals 1 minus t squared. And you have this line right here, which is x is equal to 1. Your boundaries on your x-axis seem to go from negative pi over 4 to 1, and on your y-axis from 0 to 2. So let's contemplate here what kind of representative rectangle we want to use. Horizontal, vertical, y, do we even care? Well, let's figure this out. Couple things to look at. What are your equations already solved for? Do you see that these are already solved for y? In that instance, then, you would want to use a vertical representative rectangle, but the bottom of the representative rectangle changes curves at x is equal to 0. So this would require you to have two integrals. What if you picked a horizontal representative rectangle? All right, I'm going to draw in real skinny ones. So, okay, there we go. But look, the left-hand side changes curves also, and you would have to solve this thing for t, which would give you something you really don't want, because you'd have to take the square root of both sides, and then you'd have to do arcsecant. So in this instance, I would strongly recommend that you would use vertical representative rectangles. Again, the equations are already solved for y. So let's see if we can set this up. So let's do this side first. My boundaries would be from negative pi over 4 to 0. Remember, you're sliding right and left. Let's draw a line down the middle here. Okay, you see where my functions change. Ignore your pink. So your function is only slide your representative rectangle. Let's just draw. I don't want to use that color either. What color do I want to use? Let's go back to purple. Okay, so your boundaries go from negative pi over 4 to 0 as you're sliding this thing right and left. Your upper function is y equals 2. Your lower function is secant squared t. So there's my dt. My second integral, this one right here, let's draw my representative rectangle. Here we go. My upper curve is 2. My lower curve is 1 minus t squared. Use those parentheses correctly, please, guys. dt, my boundaries go from 0 to 1. Now, you've got worked out versions of my notes, so the work is all there for the rest of this problem right here. You end up with an answer of pi over 2 plus 1/3 square units. And by the way, on the test, you're not going to have to write square units for these because you weren't even given any units to start with. All right, let's look at another one. So page 10 of your notes, you have this curve right here that's graphed for you. I believe it's blue on your notes, but I don't know for sure. And you are told that it is that super ugly function. Now, again, very, very, very beginning of part 1 of this lecture, you could have thought about this as an absolute value problem. But you do not need to, because you can think of this representative rectangle right here, who has an upper function of y is equal to 0, and this representative right here, whose representative rectangle has a lower, the bottom part of the purple representative rectangle is touching y is equal to 0. So let's set up an integral for this. I'm going from negative pi to negative pi over 2. Upper is 0. Lower is this horrible thing right here that I'm going to call f of x. Let's now do this integral right here. I'm going from negative pi over 2 to 0. Upper is this. Lower is this. Just like over here, this was my lower. And I want to get these zeros out of here. So guys, do you see that I would have negative pi to negative pi over 2 of negative f of x dx, and then from negative pi over 2 to 0 of positive f of x. Are you comfortable that those regions would be the same area? Don't know if you are or not because I can't hear you. But let me tell you that they are, and so I could use symmetry and just double one of the areas. I'm going to choose to double the purple area. Only because it had that 0 right there. Now, I'm going to show you some work for this, and then I'm going to send you someplace else to find some more work. Here is where I left off. So I'm going to replace f of x with big ugly function, cosine x, sine of a horrible looking argument. So to actually integrate this, and that's why I'm doing this with you, because I don't want you to freak out when you see something big and ugly like this and think, oh, I can't do this, I have no idea what to do. That is not true. I am going to let u equal the argument here of this trig function. So here it is right here. When I take the derivative, guys, this is just a number. This number doesn't go anywhere, and the antiderivative of sine of x is cosine of x dx. Now, do you see... Oops, I forgot something. There's my pi over 2. Okay. Do you see... Let me erase here so you can just see my work. Getting my colors out. Do you see pi cosine x dx, all of that, I can substitute in a du for? Do you see, oh wow, I'm doing my colors backwards. Oh well. Do you see this right here was my u? So I can replace that thing right there with u. Now, I want you to notice what's left. Do you see that I have a 2? And do you see that I have sine of the argument? So here goes my colors. I'm going to do my red first this time. du is going in for all the red that you see up here. Blue is going in for this. And what happened to my 1/2? Oh, this 2 and that 1/2 divided out. So all I'm left with is a sine. Remember, this 2 was from symmetry. So finding the antiderivative, I would get negative cosine of u from, here's my boundaries. Plug back in for u. So here we go. U was blue. So plugging in for blue right here. Pi plus pi sine x. Now I'm going to use my fundamental theorem of calculus. I'm going to plug in a 0 for every x. So there you see my 0 right there. And then I am going to plug in a negative pi over 2 for x. And you see it, well, you see it right here. Now, sine of 0 is 0, so that's pi plus 0 is just pi. Over here, sine of negative pi over 2, that's a negative 1. So negative pi and positive pi, that's 0. Cosine of 0 is 1. So over here, cosine of pi is negative 1. Opposite of, there's this, here's this one. Negative times a negative is a positive, so I've got 1 plus 1, which is 2 square units. Now, if you go and look at the completed notes, you will find that I have worked this problem out with this integration right here, 0 minus the function and the function minus 0, these boundaries, and add it together. And you will see on that work, which is actually a whole lot longer, that I still get a 2. So let's go on to my next page. Okay, page 11. We're supposed to find the total area of the shaded region. Guys, I want you to look at what the curves are solved for. Do you see that they are solved for x? In that instance, my gut reaction is to try to put in a horizontal representative rectangle. Now, remember you're sliding this way, up and down. So as you slide visually, is the right hand end of the representative rectangle, that red representative rectangle, does it stay on the right curve? And does the left side of that representative rectangle stay on the green curve? The answer is yes, as you slide that up and down. So therefore, I can use a horizontal representative rectangle. I am allowed to do that with one integral. So I would find my boundaries from the y-axis. So you see the 0 and the 1. I am doing right minus left. So here we go. Let's erase some of this mess. So right minus left. So here is right. Here is left. So I have right minus left. So y squared minus y cubed dy. Again, I expect you to have no issues with this integration, and you get 1/12 square units for that area. But what would have happened if you had said, hey, I am going to set this up using a vertical representative rectangle? All right, let's go back. Erase, erase, erase. All right, so let's draw in a vertical representative rectangle. All right, slide right and left. Does the bottom stay on the orange curve? Does the top stay on the green curve as you slide right and left? The answer is yes. But my equations are not solved correctly. I need to take these two equations, x equals y cubed and x equals y squared, and I need to solve them for y. So here we go. X equals y cubed and x equals y squared. I am solving both of those for y. Here I'm taking the cube root of both sides. I get y equals x to the 1/3. Here I take the square root of both sides and I get y equals plus or minus the square root of y. Excuse me, the square root of x. Here, let's write it like this for you guys for just a second. And let's go back to my picture and see which one that is. That's the orange one there. All right, guys. You comfortable that this would be, okay, so here we go. This one would be y equals positive square root of x. This one would be y equals negative square root of x. So I'm not using the negative one. So that's why you see just the positive, and I'm leaving it as an x to the 1/2 because I know I'm going to have to add 1 to that exponent. So again, I was sliding right to left. I need to subtract upper minus lower. So if you go back and look one more time, upper is your green one. It's the y equals x to the 1/3. So upper, y equals x to the 1/3 minus lower. Lower was my orange one. Y equals x to the 1/2. Let's go back and look at my boundaries for a minute. Hey, look, my boundaries here are still the same. My boundaries are from 0 to 1. I'm assuming that you can handle all this integration, and gee whiz, guess what? We still got the same area. Well, we better have gotten the same area. The region that we were finding the area of didn't change. Just how we integrated did. All right, 2 more. Find the area of the regions enclosed by the lines and curves. So you're not actually given the graph in this problem. If you go to your book, you are just given this information right here. Are you comfortable that the blue parabola is the y equals x squared and the red polynomial function is the x to the 4th minus 4x squared plus 4? So, a couple of things that we need to do. You are going to be asked to find points of intersection, and I want to be able to help you do that. So, are you comfortable? I'll go ahead and erase. Are you comfortable that you would need to set these two equal to each other? So x to the 4th minus 4x squared plus 4 would equal x squared. So x to the fourth minus 5x squared plus 4 would equal 0. This is quadratic in form, and you can still factor it. This is just x squared and x squared. I have 4 and 1. I'm looking for two numbers that multiply to a positive 4 and add up to a negative 5. Therefore, they would both need to be negative. Setting both of these equal to 0, I get x squared equals 4, so x equals plus or minus 2, and x equals 1, squared equals 1, so x equals plus or minus 1. So let's go back to this function right here. If x is 2, y is 4. If x is negative 2, y is 4. If x is 1, y is 1. If x is negative 1, y is 1. So let's find these points right here. I've got 2, 4. I have negative 2, 4. I have 1, 1. And I have negative 1, 1. Now, think about why these are important, these points of intersection. And again, if you're not given the graph, you're going to have to be able to find these points of intersection here. So copy down what you want, pause the video, and I'm going to clean off some space. So we've got our points of intersection, and we're trying to figure out why these would be important. Well, look at the area between these. You see this area in here. You see this area in here. And you see this area in here. What do you notice? Did you say that you noticed some symmetry? Okay, that's a good thing. So could you get rid of all of that and just use symmetry and double your integral? All right. Let's draw in a representative rectangle. And let's draw in another one over here. Let's make our red curve really red. And our blue curve really blue. And two questions. Number one, why vertical representative rectangles? Why not horizontal? Look at your equations. What are they already solved for? Y, correct? So that's one reason why you would want a vertical representative rectangle. All right. Number two, let's think about a horizontal representative rectangle, and I'm going to use this side of my graph over here. If I do a horizontal representative rectangle, I am sliding that thing up and down. Whoops. What do you notice? Do you see on the left-hand side, I'm blue here, but then I change to red. So I would need two integrals just for that region. Now, let's come over here, and this is really important. Okay. No problem there. Right minus left would be just fine. But put that representative rectangle down here. And what do you notice is on the right side of this representative rectangle right here? And what is on the left side? What color? Do you see that it is the same curve on both the right side and the left side? You can't have that. So you would not be allowed to do that, because guys, think about it. If you did right curve minus left curve, it would be the same thing minus itself, which would give you a 0. Okay? You can't integrate that. A 0. You don't get anything. You would get no area for all of this down in here. No such thing. You can't do that. So that's a second reason why you would not want to use horizontal representative rectangles. Okay. How many integrals do I need to find the gray shaded region that I have? Why? Are you thinking? You need to look, well, let's look first at this one right here. Do you see that the top of the purple representative rectangle is on the red curve and the bottom is on the blue curve? And then when I get over here, the top of the purple representative rectangle is on the blue curve and the bottom of the representative rectangle is on the red curve. I have to have two integrals. All right, I need a yellow one and I need a green one. Yeah, I want more room. All right, I'm coming down here at the bottom. So, all right, here's my 2 for my symmetry. And I have a yellow integral and I have a green integral. And I need a great big set of parentheses in there. So, yellow integral. All right, guys. Do you remember a long time ago we found the coordinates of that point are 1, 1? So for my yellow integral, my boundaries when I am sliding right to left would be from 0 to 1. My upper curve would be my red one. The red one is the polynomial function. And the lower curve is just the parabola. I still don't have enough room. All right, now let's add the green integral. So, upper curve is the blue curve. That is the parabola, x squared, minus lower curve is the polynomial, x to the 4th minus 4x squared plus 4. And I need a great big set of great big set of brackets. And we get a little dx in there. Parentheses, big black parentheses is outside of that. And I still need my boundaries. Are you comfortable I am going from 1 to 2? I am assuming that you guys can do that integration yourself. Again, look on my notes. You've got all the work here and on the video, and it's also on the completed notes on Canvas. There's 2 whole pages. Your area there ends up at 37/12. And let's go to our last problem. we are supposed to find the area of the regions enclosed by the lines and curves. Guys, I'll tell you right now, I am not going to ask you to graph something like this, x equals y cubed minus y squared. It is this curve right here. And you are asked to graph that, which is just a line, y equals 1/2 x, or x is equal to 2y. So as you are looking at this thing, I want you to think about how you would draw in your representative rectangle. So think. What are you thinking? I so wish you were talking to me instead of me just talking to an iPad. Okay. Do you see that you can do whatever you want right here? But in this region right here, my representative rectangle cannot be vertical. Do you see that? The top and the bottom both touch the red curve. So that one's out of here. So we have to have a horizontal representative rectangle. And you know what I'm really hoping you said? I'm really hoping you said, hey, both of those equations are solved for x, so let's draw in a horizontal representative rectangle. So both of those regions, that's what I'm doing. So remember, if you've got horizontal, you are using equations solved for x. You are sliding up and down. You are subtracting right minus left. And by the way, right minus left and upper minus lower, oh, you are going to so need those for Calc 2 at the very beginning. They're going to be your best friends. And you get your boundaries from your y-axis. And remember, your integral is a dy. So let's set up this yellow one first. So slide that in your head up and down. Do you see that your boundaries go from -1 to 0? When you do right minus left, okay, right is the red curve. It is y cubed minus y cubed minus y squared. Left, so here's right. Left is the blue curve, and it is 2y. Plus, need to add my green integral here. I am sliding from, okay, do you see I'm sliding here up and down from 0 to 2. Right curve is the blue one right here. It's 2y. Minus left curve is y cubed minus y squared, dy. Now, one thing that I have found over the years that students sometimes don't do is they don't forget to use their parentheses, like right here. And that's important because you are going to need to distribute this negative. And another thing that I have found is, not in this instance, but students tend to not combine like terms, and that makes your problem have so much more work. In this instance, there's no like terms here, and there's no like terms here. But if there were, you would want to combine those before you integrate. All right, if you have any questions, get in touch with me. Area is super important. You will be using this at the very beginning of Calc 2 when we start doing volumes. And in addition, you're going to use this idea of breaking things down into little bitty pieces and adding up whole bunches of them. Like here we're doing representative rectangles and we're summing up a whole bunch of them in an integral as they get skinnier and skinnier and skinnier. That idea is a super huge important calculus idea that we're going to use in lots of different ways. And the first way that we're using it here is in area. So this ends the second part of your lecture on area.